So try to ask as possible so that everybody can learn. All are silent. What happened? No one has any question to ask. Hello?
Hello, sir.
Yeah, yeah.
Sir, I think no question we have.
Okay, so in all previous classes we were discussing about analyzing the slopes. Analyzing the slopes. But if you look at very carefully, in all these cases where the C5 analysis or pi is equals to 0 analysis, or when you dealt with Taylor stability number, what we have done is we made an assumption that all the slopes are homogeneous and made with a single soil. And moreover, so we did not try to distinguish between layers or what happens if the soil as a layered soil. So these are the couple of the assumptions that we inherently made it. Okay. On the other hand, what or how to determine the stability of a slope, or how to determine the factor of safety of a slope when it possesses multi-layers, as we can see in this picture. So this is called as a non-homogeneous slope, where it comprises of several number of layers, and each layer having its own values of density and shear strength parameters such as C and pi. Or the irregular slope, where the slope angles are different for different heights of the embankment or different heights of the overall slope. Then in these cases, how to determine so the factor of safety. So here we take the advantage of another method. So those are called mass residue, because we have considered the whole slope area into a single mass, and thereby we have assigned or represented the entire mass of the slope as W. So those are called as a mass procedure. And this mass procedure is further accompanied by the moment equilibrium. So we know the weight of the whole mass of the soil, and we know the lever arm distance at assumed center of the circle. So if you take the moment over the center of the circle, then what we get is we have taken the moment equilibrium between the weight of the soil and the resistance offered by the soil. So this is called as a moment equilibrium. But there are some methods which also considers the force equilibrium. But when you want to consider the force equilibrium, so we need to analyze or we need to do another procedure, the method of slices. Now here onwards, you could see a variety of methods. So that would be useful for analysis of different variety of the slopes, considering with and without the pore water pressure. And when the slope is for a particular purpose, for example, if you look at the canal, there is a problem called as a sudden drawdown. And if you look at the reservoir, this kind of a drawdown is rarely occurs, but the bonding of water is forever. So it is a constant. That means you can anticipate a constant amount of seepage in case. So undrained analysis and other cases where there is a possibility of the development of the pore water pressure because of the only overburden. So in these circumstances, or when these kinds of the slopes are encountered in real life, then how to determine the desired factor of safety. So in these circumstances, it is not only the moment equilibrium that suffices to determine the factor of safety. So we might have also need to consider the moment plus force equilibrium together. So depending upon the consideration given to moment and force, different people evaluate different equations. Summarize all these things at the end of the slope stability. Who has considered the moment equilibrium alone, the force equilibrium alone, and moment plus force equilibrium together? So there are several people. Okay. So considering the importance of the PG program, I'm going to cover very vastly all the slope stability. So I may take another 4-5 lectures only on the slope stability. Bear with me because you need to understand the very fundamentals of all these things. And so far what we have discussed in the last 2 classes over the slope stability, those are only fundamentals. Okay. So those will give you the worst factor of safety value. But if you want to determine the factor of safety of exact value, then we must resort to the process called as the method of slices. So now let us try to discuss how these methods have been evolved over who has contributed for what for the maximum and for different slopes. So here we can take in method of slices. So this is a typical slope. So that should be analyzed. So this is a slope, and where this blue line A and C is probable failure plane. Blue line, this arc line ABC is a probable failure. C is assumed the center of the circle, and the given soil mass is divided into so many number of slices. However, there is a contrast in the opinion. Do we need to take equal width of the slice or different width of the slice? So, but most of the people concluded that it is better to consider equal width of the slice. However, there is no constraint on how many number of slices one need to consider. This depends upon the kind of the program that you are dealing with. If you are considering more and more number of slices, so the program may take a little bit time for analyzing all the forces and moment equilibrium. While if you consider least number of slices, then it is a quick. So this is only the difference. If you consider more number of slices, you need to analyze more number of mathematical equations. And if you consider less number of slices, less number of mathematical equations. So as you can see here, there are other assumptions also. The soil mass above the trial surface, that is A, B, C, is divided into several vertical parallel slices. Vertical parallel slices. The width of the slice need not be the same as I told you. So the accuracy of calculation increases, number of slices are increased. So this is obvious. If you take more and more number of slices, you will get better and better factor of safety values. So there are some assumptions also. The inclination of the base of the horizontal is alpha. So this is called as this failure plane. Suppose if you take this is approximately alpha and the height measured at the center h. So for the sake of simplicity, it is assumed that the width of the slice is b and height of the slice is h. So that is the one of the reason in all previous analysis cases we have taken the width as a b and height as h. Height is h. Now another complexity also we can see here. Suppose as I told, so in the mass procedure we have considered the entire area of A, B, C and A as a single mass, that is weight. But when you resort to method of slices where you are dividing the given slope into so many number of slices, you can see are evident here. So the weight of the each slice is different and the lever arm distance of the each slice also different from the center of the circle. This is the center of the circle. So if you draw a vertical line, so on the right side there are couple of number of slices, on the left side there are another couple of number of slices. Now you also try to understand the value of the alpha is not remained constant. This also varies and its sign also varies. On one side it is positive, on another side it is negative. On another side it is negative. So then accordingly couple of the slices act against the slope, that they cause slope instability, while the other number of slices may act against, that means they cause stabilization. That means majority of the slices will become driving forces and a couple of the slices will become the resisting forces. So this is how they contribute, and this is the beauty of the method of slices. And remain equations, the form of the equations or the constitutive laws are remain same for mass procedure and the method of slices. There is no difference. Simple slope that has been taken for to analyze by resorting to the ordinary method of slices. Different normal stresses means shear resistance would also circle. Also different, and since our sine angle is different, then your lever arm distance also varies from slice to slice. So these are some general guidelines for slice selection. Slices do not have to be of equal width. So this is reiteration. You can take of equal width or different width, but for the simplicity, it is always advisable to consider so equal width of the slice. But even if you take the unequal width, there is no problem exactly, because nowadays everybody is solving all slope stability problem with the help of a computer programs. So therefore there was no manual work involved in it. It doesn't matter whether you take the equal width or unequal width. So for convenience, base arc of the each slice should pass through one soil type only. One soil type only. So slice width should be limited. So these are some important assumptions. And this is the free body diagram of a single slice where the width of the slice is B and weight of the slice is WT, and the inclined length at the base of this slice is L. So if you draw the free body diagram of this slice, so W is a weight, and when W is acting, the resisting soil develops two counteracting forces. One is tangential, next is normal. So the angle made by the resultant with the normal force, is alpha. So this alpha is also different for different slices. So I know the horizontal width of the slice B, which is B, then I can able to calculate the inclined length of the slice. So that is L. There is also is perfectly inclined, but in reality it is not inclined. It is a curve. If you look at this curve, this is an arc. But if you look at the slice, so this is a linear line. So there is an inherent assumption that so the base width of the slice is somewhat linear, or it is only linear. But since the width of the slice is infinitesimally small, so even this assumption, if you keep on submitting up all the slices, then again it makes the arc. So it won't make any kind of a what do you call a linear line, because your angle is varying. So angle is varying. So the same principle of your mathematical analysis is valid here also. So in reality, we can never able to draw any kind of a circle. So we divide the circle into so many number of infinitesimally small elements and join them all, then thereby it forms the circle. So the same simple analysis is valid here in this case. So the factor of safety can be defined as the resisting moment by the driving moment. Here as we know, so the resisting moment is the shear strength developing all along the arc length, that is S, multiplied by the lever arm distance. Now in the mass procedure, we have only single weight of the soil mass and a single lever arm distance. But in case of the method of slices, we have n number of slices. Therefore, we have n number of weights and n number of lever arm distances. So therefore, we can say summation of the weight multiplied by the lever arm distance. Since we know the lever arm distance from the center to the corresponding slice, so the computer program easily calculates and thereby sums up to calculate the combined resisting moment while our driving moment. Okay, so the factor of safety is defined as resisting moment by the driving moment. I know the width of the slice as a B, and using this simple mathematical jugglery, I can able to calculate the inclined length of the slice. So that is L is equal to B by cos. Is the intensity of MD. So let us take the TR as the total shear strength, or total shear strength or shear resistance developing all along the length of the arc. So total shear resistance force acting in the slice. So this is force and this is strength. Strength is force divided by the area. So this is a force, that is shear force, and this is shear strength. This is shear stress, this is stress. So force is nothing but strength multiplied by unit area. So here unit area means the length of the arc is known. The length of the arc is L. Then the unit length will be taken the perpendicular to the monitor. So that is a unit meter. We always make this kind of an assumption all over the geotechnical engineer, or in fact for the civil engineer. So L multiplied by the 1. So stress multiplied by the area, that will again give you the force. So the TR is nothing but tau R multiplied by L into 1. So this is 1 can be ignored. So the total shear resistance is nothing but TR is equal to tau R is total shear strength, that is C dash plus sigma and tan pi multiplied by R. So if you take tau R is equal to TR by L, again we will end up at the same previous class discussion where we have derived in case of the infinite slope. So tau R is equal to force upon area. So tau R is equal to TR by area. So both are same. So next, try to calculate resisting moment. Mr is equals to Tr multiplied by the R. So this is the total resistance R along the slip circle, and R is the lever arm distance. So in fact, for resisting moment for Tr, the lever arm distance is constant because this is a circle. So that is R. That is R. So Tr is equals to tau R into 1. So this is simplification. And sigma n, that is a normal stress. So which is nothing but the weight of the soil divided by the area again. So here, if you look at this slice, and if you draw the free body diagram, and if you resolve the forces in the direction of the normal stress and the shear stress, what you will get is Wt cos alpha and Wt sin alpha. So in the direction of normal stress and shear stress. So if you want to calculate the normal stress, sigma n dash, which is a part and parcel of the Tr, so then this is nothing but total weight of the slice. So Wt cos alpha is weight of that particular or one particular slice divided by the length of that particular slice into the unit length 1 meter. So Tr is equals C dash into L, where capital C is total cohesion all or over the entire length of the arc AC or AB. So usually capital C dash is written as small c into L, where small c is the cohesion component of the soil. Small c is the cohesion component of the soil. So if we multiplied cohesion with the total length of the arc, then what you will get is total cohesion plus sigma n dash tan pi. So here also, so Wt cos alpha by area is already known. So this is normal force multiplied by tan pi multiplied by the length. So then if you simplify this one, what you will get is Tr is equals to C dash L plus Wt cos alpha tan pi. So if you multiply or with a lever arm distance, what you get out of it is total resisting moment. Mr is nothing but R multiplied by Tr. Tr is C dash L plus Wt cos alpha into tan pi. So then we have seen the driving force. So driving force is weight of each slice multiplied by again the lever arm distance R. So Md is equal to R into Wt sin alpha. R into Wt sin alpha. So if I know Mr, if I know Md, so then factor of safety is nothing but Mr divided by Md. So Mr is known, Md is known. So then try to substitute into the factor of safety equation. So what we will get is C dash B secant alpha plus Wt cos alpha tan pi by Wt sin alpha. While this Mr and Md, which we have derived, are corresponding to a single slice. So it has to be extrapolated to so many number of slices depending upon the number of slices that we have assumed. So therefore we can take the summation on the numerator and the denominator. So therefore factor of safety is nothing but summation of C dash B secant alpha plus Wt cos alpha into tan pi. You may find different forms of factor of safety equation for ordinary method of slices. Okay, so but don't get confused. So the same remains same. What you need to understand is, so how should or what is the slice that I should consider, and how should I draw the free body diagram of this particular slice. So then once you are understanding these two, then you can easily able to derive the equation for the factor of safety by the ordinary method of slices. But anyhow, so these methods are no more in use because this is highly simplified method. Now another important distinction that can be made between ordinary method of slices and the previous methods like pi is equals to 0 analysis is that if you look at the ordinary method of slices, only one another simplification was done. That is, we divided the whole mass of the soil above the slip failure into so many number of slices. That means we are assuming that each individual slice is acting independently. Now, when each slice acts independently, there should be a development of normal and shear force at the interface of the each slice. Holistically, there should be development of normal and tangential force at the interface of each slice. Okay, so the major assumption of ordinary method of slices is that there was no development of normal and tangential forces at the interface of the slices. So this is the reason nowhere we have considered any kind of interface of the tangential and normal forces between two slices. That's why it is called as a ordinary method of slices. Okay, one more thing also you need to understand. When I have considered different slices for analysis purpose, the weight of each slice is different. When weight component is different, it is obvious that the normal and tangential force that should means act on its subsequent slice must also be different. It is not remain same from top to the bottom of the slice. It always depends upon how much amount of force is getting nullified and how much amount of force is getting transmitted from upper slide to lower slide or lower slide to upper slide. Okay, so since the ordinary method of slices doesn't consider any of these things, it is called as the ordinary method. So, but in the previous slide, we have considered only this purpose. But what is the exact meaning of the factor of safety? The meaning of the factor of safety is that it is the least value can undergo the failure. As we have understood from all the previous classes, if the factor of safety is 1, so the slope is on the verge of a failure. Now, how to bring it the factor of safety from 1 to the desired level, say 1.5 or 1.3 or 2. So, as per the guidelines of the codes or the standards. For that purpose, you need to make numerous trial circles as shown in this picture. So, you need to make a numerous trials. Okay, but if you keep on doing all these trials manually, so maybe your entire life is insufficient to calculate the factor of safety of a single slope. So this is where we need to understand the requirement of the software or other mathematical analysis, where the software should do the analysis and should give us where is the location of the most critical slip circle at which the factor of safety value is least. As we can see here, so the factor of safety for this circle it is 1.79. For example, if you again you need to consider all varieties of the failures: slope failure, toe failure, and base failure. And depending upon the assumed trial slip circle, your factor of safety value also varies. Okay, suppose if you want to again try to understand the intricacy. If I want to understand the safety against only slope failure, then I have to take numerous numbers of trial slip circles all along the length from A to B. Then if I want to repeat the same thing for the toe failure, then I have to assume that trial slip circle is passing through the toe. However, if you look at the top of the berm, where should it emerge? Should it near to the edge of the berm or at the far end of the berm? So we don't know. So thereby we need to consider again numerous number of trial slip circles. Similarly for the base failure. Now if you keep on considering all these numerous slip circles, you will be ending nowhere. So that's why it is really impossible to determine the factor of safety by the manual way of any slope. This is one of the fundamental reasons we must stick to some kind of the programs for determining the factor of safety, whether it is ordinary method of slices or Bishop's method or pi is equals to 0 analysis. It is immaterial. But at the same time, you must understand that one has to take numerous numbers of trial slip circle in order to arrive at the least the trial slip circle which is has been given with several people. So this is case 1. So this is valid for the soil, cohesive soil, where pi is equals to 0 analysis. Try to assume, and the first initial assumption is this is a toe failure, toe circle. And here we need to know the two angular values. One is theta 1 and theta 2. Theta 1 and theta 2, as you can understand here. So these two angles are making at the toe and at the top of the bar with respect to the center of the circle. So first plot the configuration according to scale. Draw the two lines from points A and B. Point A is toe of the slope. Point B is top edge of the slope at an angles as been shown in the figure. So that is theta 1 and theta 2. So taking radius equals to OA. So draw a circle passing through the slope. So this can become critical slip circle. However, the slope AB is not remain same. We can go for 1:1, 1:2, or 1:1, 1:1.5, 1:2.5, 1:3, so on and so forth. So therefore, how do I know that what would be the value of the theta 1 and what would be the value of theta 2? So for that purpose, people has given different values of theta 1 and theta 2 depending upon the slope that you want to consider. For example, if your wish is to consider one vertical to 0.5 horizontal and the slope angle is approximately 60. So the 60 is not theta 1 or theta 2. So this is 60. So this angle is 60. This is called as a slope angle. If slope angle is 60, then theta 1 is this one and theta 2 is this one. Okay, this is again simple mathematical jugglery. You can look into it. So if your slope is 1:1, that is 45 degree, then theta 1 become 28 and theta 2 become 38. Okay, so when people has recommended different values of the theta 1 and theta 1 and theta 2, this does mean that they might have made several number of trials to arrive at theta 1 and theta 2. So therefore you have to assume that proposed based on their experience or based on their practical trials, so that they have made it. While you need to be very cautious that again, so probably give you the least factor of safety value. It is always advisable to go for your intuitive justification whether this is really true or not. But probably this might be giving the least factor of safety value. That might be true. So then in case of base failure, because in the previous case we have seen the toe failure, in case of the base failure, then we can follow this one. So you have to assume that center of the circle is acting. So at h by 2 from between the A and B distances, h is the total height of the embankment. So then identify a distance of h by 2 and h by 2 between A and B. Plot the configuration according to the scale. Draw a vertical line at the midpoint of the slope. Draw a vertical line at the midpoint of the slope. The center of the critical slip circle always lies on a vertical line passing through the midpoint of the slope. So this is also based on the understanding. So nobody says that this can happen here. But when they have analyzed numerous number of slopes, people did observe that probably the center of the circle might be happening at the mid slope. Okay. Determine the center by hit and trial method by comparing the factor of safety. So again, so I'm reiterating, this is a trial and error method. So hit and trial method. Circle with the minimum factor of safety value is the critical circle. So angle made by the critical circle at the center is about 133.5 degree. 133.5 degree. But so this is as per the Fellini's recommendation. Now, so probably since you are a student, so you have to understand there might always be a wrong concept that the slope failure always occurs when the volume of the soil is very large. Meaning thereby, suppose if you compare the area within this red circle and area within this blue circle. So it is obvious that the weight and area of the soil, so lying within this blue circle is higher than the red circle. But incidentally, the failure is happening within the red circle. Okay, so therefore remove a kind of a misconception from your mind that the failure happens only when the soil mass weight is very high. That may not be the possibility, because several students might think that the factor of safety means, since we always discuss about the weight component in all the equations, so therefore if I take bigger area and therefore bigger weight and therefore more is the possibility of the failure. That may not be true. You have to assess different other conditions. So then this is for C5 soil. We have base circle failure in case of the cohesive soil, and this is in case of the C5 soil. So here the procedure is for uh, uh, in the base failure we have divided, or we assumed that uh, the center of the circle is passing through the midpoint, however in the vertical direction. But in case of the C5 soil, the direction of this line is inclined. It's not the vertical. So here in this case, you first draw an horizontal line. So below the base of the embankment, so which is at a depth of h plus h, 2 times of the height of the embankment, as demonstrated here. Then you need to draw two cards or two lines with respect to theta 1 and theta 2, or with respect to A and B with an angles of theta 1 and theta 2. So find the intersection point of 4.5h. So this is 2h and this is 4.5h from point A, and h distance vertical from down A. So when I know 2 times of h, when I know 4.5 times of h, I could easily identify the point C. So draw the direction angle theta 1 and theta 2. So draw the direction angle theta 1 and theta 2. So join the points of intersection O and C. So join the points of intersection O and C. So locate theta C, that is C designates critical by hit and trial. For this, try O1, O2, so and by making several number of trials. The circle giving minimum factor of tail is the critical circle. Now here theta 1 and theta 2, we supposed to take it again from the case 1, where pi is equals to 0 analysis, because this also passing through 2. So that means the theta 1 and theta 2 values are depending upon the slope angle, whether it is 1 is to 0.5 or 1 is to 1 or 1 is to 2 or 1 is to 3 or so on and so forth. Okay, so that's what all about the ordinary method of slices. So I think Bishop's method probably I will cover in the next class. So let me try to end it here only. So these are the most important. I should give enough time for understand. So if you have any questions, you can ask me.
Sir,
Yeah.
sir, the slicing is done in vertically, sir.
Yeah, slicing is always done in the vertical direction.
Sir,
Preferably.
if it is done in vertical direction, then if we consider a single slice, then there will be
Yeah.
layering in that slice.
Correct.
So by that also we get different gamma values. So
Yeah,
what's
that's
the
that's what's shown here. Na? Suppose if you look at here,
yes, sir.
so we have divided in the slices in the vertical direction, but there is soil layers also, layer 1, layer 2, layer 3, layer 4.
Yes, sir.
So we have, yeah, accordingly you have to take different weights corresponding to different layers.
Sir, so we have to take some gamma average for the weight.
No, we don't need to take gamma average. It is again, gamma is summation of again gamma 1, gamma 2, gamma 3, gamma 4.
Okay, sir.
Okay, like for example, if you look at this slide,
Yes, sir.
so corresponding to this slide again, summation of layer 1, layer 2, layer 3, layer 4.
Okay, sir.
Okay, the lever arm distance may be same, but the weight component is different and gamma is different.
So individual weights have to be added to get the total
Yes,
weight of that slice.
correct. But this
Okay.
only makes it more complex.
Yes, sir.
That's why we need to go for computer program always.
Okay, sir.
Sir, which software is applied for this?
Pardon me?
Sir, which software is used to analyze this slope?
Software. Oh, there are several. There are more than 20 or 30 variety of softwares. Okay. You can. There is a software called as GEO5, which is available at the free of cost. You can use it. Otherwise, there is a Slope W. There is Geo Studio. There is a Rock Science. There is Slide 2D, Slide 3D. Then everybody, you can also develop your own program because you know the fundamentals. So you know the equations. Once equations are known, it is quite easy to develop your own program. But different people have a different programs, but all are not same. The validity also different.
So
Yeah.
you are saying that in the method of slices, like some slides are actually contributing or they act as a driving force, whereas some act as a resisting force. So is that true in all the practical cases?
Yeah, it is true.
So the entire mass won't be contributing, like it won't be a resisting thing or it won't be a driving thing.
No. But majority is a driving thing, and small number of slices are acts driving
Okay.
forces.
Okay, sir.
Sir, in the last
Yeah.
slide
Yeah.
of today's class, can you go to last slide?
Yeah.
Yes, sir. Sir, in this slide, sir, this 4.5H and H, the point C.
Yeah.
Sir, what is the significance of this point C?
See, uh, based on based on this case one, I know the theta 1 and I know the theta 2 values from this table. Okay, but here also I can locate the center of the circle, but this only gives the toe failure for pi is equal soil, the cohesive soil. Okay, so if I want to deal with C5 soil, so then what should I do? You understand? So if I take only theta 1 and theta 2 and I can able to identify the center of the circle, so this replicates the case 1 where pi is equals to 0. But in case of the C5, the same case 1 has been extended to be valid for C5 soil. But in that case, so they have drawn an inclined line. So where the center of the circle is known. Now another point they try to identify, which is approximately at a depth of 2h and a width of 4.5h. And I do not exactly know what is the significance of the point C. But this is the procedure they proposed.
Means 4.5H and this 2H value is they have assumed.
Yeah, it is based on their practical experience.
Okay. It is a fixed value.
It is a fixed value, correct.
Sir, we are just changing the point O according to the line.
Because this line is fixed now. This line is fixed. So if I take O1, the trial slip is different. O2, trial slip circle varies. Then correspondingly, the factor of safety also varies.
Okay, sir.
Okay. So I will stop it here. So then we will meet next what date? Next Tuesday?
Yes, sir.
Okay. So we'll meet on next Tuesday. So there I can elaborate.